Okay, should be recording now. Hi, my name is Frank Zhang. I am currently a senior in the Department of Electrical and Computer Engineering. Today, I'll be sharing some of my works on constructing a type binding model for the alpha and beta phase of gallium oxide and aluminum oxide. So as an introduction, beta gallium oxide, alpha gallium oxide, and alpha aluminum oxides are what's called emergent ultra-wide bandgap semiconductors. The fact that they are wide bandgap semiconductors makes them very advantageous, actually orders of magnitude more advantageous than silicon in power electronics, high frequency electronics, and they also make UV photonics in semiconductor possible. Studying electrical and photonic devices made from these materials requires careful modeling of their material properties. And currently we have several ways to do that. We have the more modern way of density functional theory, or DFT, that gives you the full electrical and optical properties, but they are generally very computationally expensive. It takes 1 hour on 24 processes to run this model. On the other hand, you can have very simple model, such as effective mass approximation. They are computationally very efficient, but they only gives you the low energy features of the electrical and optical properties. So we want to have a model that is both computationally efficient and describes the full electrical and optical properties of these materials. That's why we come to the type binding model, which can generate the full electronic structures in a very simple matrix. Because it is a simple matrix, it is computationally very efficient. It usually takes you 1 second to solve the model. And it describes the full electronic structure with a broad energy scale. And it also gives you a physical and chemical intuition. So if you go to the tiny cartoon here, this cartoon has 5 atoms, each with an energy called epsilon. This is what we call the on-site energy. This kind of corresponds to the potential energy for electrons staying in that atom. Now, electrons can move around between atoms, and the energy cost in moving around will be described by negative T, which we call the hopping energy. That's something describing the kinetic energy of moving electrons. Or another way to think about that is to make a chemical bonding between adjacent atoms, and this bonding energy will be around negative T. Okay. Now let's talk about how do we derive our type binding model. We derive the type binding model from the DFT calculations, which gives us the full electronic structure, but then we want to make some simplifications. And the way we do that is to calculate what is called the maximally localized Wannier functions. That will generate for us the wave function for the maximum localized Wannier functions, which gives us the on-site energy, epsilon, the energy scale of the wave function, or the potential energy. And also generates the chemical bonding between adjacent Wannier functions. That gives us the hopping energy T, or the bonding energy, or the kinetic energy. Either way is fine. So I'm plotting here the crystal structure of the materials we're studying: gallium oxide, beta phase, and alpha phase gallium oxide or aluminum oxide. And then I'm also plotting the resulting 1A functions we obtain from the DFT calculations. As you can see, the 1A function has a very interesting shape that echoes the local chemistry environment. So if you look at this one, the 1A function is centering at the green atom, which is gallium, and there are also some minor lobes centering at the red atoms, which are oxygen. So in short, wave function, 1A wave function will echo the local chemical symmetry. All right, see some results. In the first row, I'm plotting the DFT band structure of the 3 materials, and band structure is basically equivalent to electrical and optical structures and properties. And I am labeling different band with different color because they correspond to different atoms at different orbitals. Now, if you go to the second row, I am plotting the band structure generated from type binding model, comparing with the DFT band structure. What we want is to have the type binding model reproducing the DFT band structure as best as possible while making it computationally cheap. That means we want to make some simplifications. So first, if you look at the higher part of the upper band, these regions are not usually accessed in typical laboratory energy scale, so we throw them away. And also the lower band, deep inside the band, these bands will make no contribution to current conduction. So we also throw them away. Now, near the edge of the lower band and upper band, these are very important to the major electrical and optical processes. So we want to make them as close to the FT band structure as possible. And as you can see, we did a pretty good job at mimicking most of the features here. Okay. So in conclusion, we have derived a type binding model from DFT calculations using maximally localized finite functions for these three technologically relevant materials: beta gamma oxide, alpha gamma oxide, and alpha alumina oxide. We have reproduced the features in the band structure that are relevant to the major electrical and optical processes. That means we can use this model to study some interesting behaviors in various forms and structures of these three materials. We can study the bulk material under different conditions, different orientations. We can study different electrical devices, optical devices. We can put different materials together to form heterostructure. And we can also study their behavior in a quantum limited regime. So in short, it's a very versatile model. You can do all kinds of things with it. But meanwhile, you can also keep the computational cost very, very low. Okay, that's it. Thank you for your attention.